Let's suppose we've got a convergent alternating series. And in fact, let me say that the sum of this series is S. And so we could say S is equal to A1 minus A2 plus A3. And we could keep going on and on with that, um, minus A4 plus minus all the way out to some A sub big N. Okay? And then, the next terms in that would be A sub big N plus 1 minus A sub big N plus 2 plus A sub big N plus 3. And you can see, and it goes on and on forever. It's an infinite series. So let's suppose that we've got this situation. That's the sum. And what I want to do, I want to look and see if I just consider Sn, the nth partial sum, how does that compare to the total sum? In other words, when I take the sum minus the big nth partial sum, what's left over? I mean, how big of a difference can that be? And I'm going to call that the remainder. The, the remainder, the big nth remainder. Okay. And the question is, well, how big can that possibly be? How big can R sub big N possibly be? Well, think about this. Think about if you just and let's just look at the positive parts of this. Let's just absolute value it. We'll get the absolute difference here. Now, if I do take S minus S sub n, what I'm doing is I'm subtracting off all this part right here. And this over here is the remainder. That's the remainder right there. So the question is, how big can that be? Well, think about this. Now remember, every term is getting smaller and smaller and smaller in this alternating series. So this A sub n plus 1 is bigger than the A sub n plus 2. Now think about what's happening here. Let's just put some numbers to these. In other words, A sub n plus 1, let's just think about what's happening. With A sub n plus 1, you're subtracting off A sub n plus 2. So you get a little smaller. But don't worry, you're adding back A sub n plus 3. But you're not adding back as much as you subtracted off, right? A sub n plus 2 is bigger than A sub n plus 3. So you subtract off A sub n plus 2, and you don't add back enough to make up for that. Okay? So this thing, this remainder, the biggest this remainder can ever be is A sub n plus 1. So what we're saying, what is obvious here is that this right here has got to be less than A sub big N plus 1. In other words, that big nth partial sum, if we want to know how good of an approximation is that to the entirety of the sum, the difference, here's what we know. The difference, S minus S big N sub big N is less than or equal to A sub big N plus 1. So this tells us if we want to know, okay, well, I'd like to approximate this sum, but I don't want there to be too big of a difference. In other words, if we have a specified tolerance, an error that we're willing to tolerate, we will know how many terms or we'll know how many terms to carry the sum out. So let me show you an example. So suppose we have this alternating series and we want to approximate the true sum so that the error, so that the difference between the actual sum and our partial sum, we want that to be less than or equal to, let's say 0.001. So we're looking for the term, we're looking for the error term that will be less than or equal to 0.001. So we want to know, well, how far out to go. So we have some choices here. Here's n, and Down here is 1 over n to the fourth. And I'm going to let n be 1. I'm going to let n be 2, 3, 4, 5. And I'm just going to see how far out do I need to go before I get that error that I'm looking for. So, of course, when n equals 1, we just have 1. Okay? When n is 2, we've got 1 over 2 to the fourth. 1 over 2 to the fourth. And 1 over 2 to the fourth is 0.0625. Okay, 0.0625. Now, we put in a 3, and we've got 0.0123, you know, rounding. And we put in a 4. So if I put in a 4, I get 0.003. Now remember, we want 0.001. So if I put in a 5, it looks like that might do it. And I'm just punching these in my calculator. Well, that is not exactly, I'm not there yet, okay? Because I want 0.001, and this is not quite there. So let me try 6. So if I put in a 6, 1 over 6 to the fourth. Ah, that does it, because it looks like I've got 0.0007. That's less than 0.001. So my error, so here's what I want to do. I'm going to approximate this way. N goes from 1 to 5. That's what I'm going to use to approximate that sum. And the error term is the a sub 6, which is, well, I'm just looking at the absolute value of the error term. It's 1 over 6 to the fourth. So let's take a minute and dig what we've got here. We've got this, that if you take the true sum minus the fifth partial sum, that's going to be less than or equal to 1 over 6 to the fourth. That's what we have. Now, so, and notice it was very easy for us to do that. Now, we could have done this a little more algebraically. Here I've just kind of done it trial and error, but uh, we'll just go with it that way right now. Okay, now what does this mean? This means that if I drop the absolute value, I've got this. Right? And then, of course, I can go a little further. I can say, well, then I've got S sub 5, the fifth partial sum, minus 1 over 6 to the fourth is less than or equal to the sum, which is less than or equal to S, the fifth partial sum. Okay? So notice what we've done here is we've got an interval. We don't know what the true sum is, but we do know it's between this number and this number. And of course, we can compute the fifth partial sum. And of course, I can compute 1 over 6 to the fourth. So what I have here is I have an interval that I can box in. I don't know what the sum is, but I can box it in, and I know the smallest value it can have, and I know the largest value it can have.